Alright, so today we got something special for you. The famous world-known Pythagorean Theorem, which says if you've got a right triangle like this one, you got one of the sides is A, the other side is B. The one across from 90 degrees is usually called the hypotenuse. If you've got a right triangle like this, it is always the case that A squared plus B squared equals C squared. That, my friends, that's what you learn in grade school. Everybody knows it. And what we would like to do today is figure out exactly why that's true. But again, most of you know the theorem, or you've seen it. You know that if you got any two of the sides, Pythagoras will help you find the third one by plugging it into that equation. For example, if you knew the A and the B, you could figure out the C, or if you knew the C and the A, you could figure out the B. Today, what we want to do is answer the question why. Why is that true? And so to do that, here's the game plan. We take this triangle and we make another copy of it, and then 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 we make a little piece which is a difference of these two sides, and then we arrange it. We arrange these this way, and then we rotate them this way and that way and that way until we make a big square. Whoa, there's a square. This big square has a little hole in the middle. But no worries, that's why we got this other piece here. And that, my friends, that's a big square. Okay? And that's the amazingly creative idea, to take that big square and then to look at that big square in two different ways. Specifically, we're going to look at the area for that big square. On the one hand, let me see if I can zoom you out of there just a little bit. On the one hand, that's a big square where the sides are C and C, and so this area will be a C square quantity. That's this side C, and this side C, and that side C, and this side C. On the other hand, you've got a triangle, and another triangle, and another triangle, and another triangle, and the little piece inside. And so the idea is that to look at this shape and look at the area of it two different ways. Over here, the area is C squared, but it must be equal to the area on this side because it's exactly the same area, just cut into little pieces. And this area we can figure out using the formula for the area of a triangle. Base times height divided by 2. So it's 2 times base times height divided by 2. By the way, that's also an interesting question. Why is that always the case, that the area of a triangle is base times height divided by 2? But we'll let that slide this time. We'll let it slide. We'll cover that maybe a different day. Anyways, it's base times height divided by 2, but I have 1, 2, 3, 4. So I really have 4 of these, four of those guys, plus I have a little, I'm going to put a plus here, 4 of these, plus a little guy in here. Now let's look at that in our picture. This is the bigger side on my triangle. This side is B, and this side is A because that's the smaller part of the triangle. This is B, this is A, this is B, A. So therefore this guy right here is B minus A from here to here. That makes it B minus A here and B minus A there. So this one is B minus A. Let me zoom you in there. That makes this piece right here B minus A by B minus A. So this will be B minus A, the quantity squared. That makes it, the left side is C squared, and this side would be 4 times B over A over 2. That means the same thing as 2 times BA. And then you've got to expand this binomial using your excellent algebra skills. You know that you could FOIL that if you wanted to. You'd get something like this. And then what happens? Well, then this would clean up nicely because if you have 2 BAs and you take away 2 BAs, well, all the BAs are gone. And lo and behold, what you've got here is that C squared is equal to A squared plus B squared. See that? That's why they pay me the big bucks, my friends. That's Pythagoras theorem. Okay. And if you weren't convinced by that, let me show you a second look at it. 2 for the price of 1. Watch this. Here's another look at it. To say that A squared plus B squared equals C squared, that's to say that if I take a square where one of the sides is where the square is this side by that side, A by A, and I look at the b square, this would be the area that we could shape that we could use to represent the area of b square, or the quantity b square, and this one represents a square. What does it mean when people say a square plus b square equals c square? It means that if you add these two areas, you get the same as a c square. So in other words, when people say a square, we say a square plus b square equals c square, we're saying that the sum of these pink areas, the a square plus the b square, is the same as that. Let's look at that. We're saying that if I take a square plus the b square, it's got to be the same as that. That's what we're saying. We're saying that this guy plus that one is equal to that one. Now, how in the world are we going to prove that? Well, we already proved it once, but I thought it'd be fun to try it a different way. You could do it with exactly the same four little pieces. Let me show you how it's done. All right, don't try this at home. This is very dangerous, but I'll try to proceed with caution, and let's see if we can do it. So here's another look at it. I got to show that a square plus b square equals c square. I got to show that the size of these two squares is the same as the size of that square. So here's one thing I could do. If you realize that if I switch these, that doesn't change the size of them, nor will it change if I put these together. Now it looks more like that one. Not really, I'm just kidding. It still doesn't look like that. Here's what I got to do with this one. I'll slice it up the same way. I slice it up the same way I had it before, and then I play this excellent game here. I could take this one and put it here, and I could take this one and put it here. Whoa, 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 no way. No way. This can't be happening. Lo and behold, are these two the same? There's no way they could be the same. Whoa, 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 maybe they are. In fact, they are exactly the same. I told you, a squared plus b square equals c square. That's why they pay the hands, buddy. Take that one to the bank. Alright, we'll see you guys here next time. Peace. Now, how we actually use it, this is how we use it. Every time you've got three sides on a triangle, which is almost every time, and you know two of them, but you want to know the third one, it's Pythagoras time. It's always Pythagoras time when you want to know the third side and two of the sides are known. Here we go. We got two sides. You got a right triangle, so you're okay to use Pythagoras. You got one side that's unknown. Pythagoras would say, hey, I got this one. X squared plus 3 squared is equal to 7 squared. And that would tell you that x squared plus 9 is equal to 49. And then you could subtract 9 from both sides, and that would tell you that x squared is equal to 40. So then x would have to be plus or minus the square root of 40 by the square root property. And if you're just looking for length, not the direction of the length, we could just interpret this as having that this must be the square root of 40. Sometimes you may be interested in the negative direction. That may not be now, but that's how you use Pythagoras. Every time you know two of the sides and you want to know the third one, it's Pythagoras time. Let's do that again. Suppose this time you know one of the legs is 1 and the other leg is 8, but you don't know the hypotenuse. No problem. You know two of the sides. You want to know the third one, it's Pythagoras time. So Pythagoras would say 8 squared plus 1 squared is equal to x squared. And that would lead you to the conclusion that 64 plus 1 is equal to x squared, which would then imply that x squared is equal to 65, which would then imply that x equals plus or minus the square root of 65. If you're looking for strictly the length of it, you'll interpret that as the length would be the square root of 65, and then you'd be done. And again, there might be occasions where there might be some deeper interpretations of the negative number. This may not be the right place for it, so that's another example. There's plenty more where that one came from. Maybe we could do one more, and this one a little bit more interesting. Here's a problem for the ages. It has to do with our beautiful Earth here. And have you ever wondered how big is the Earth, or how would one go about calculating the radius of the Earth? Here's a little proposition for you. Suppose you go on and you try to find the biggest mountain in the United States, and then you figure out that the biggest mountain is Mount McKinley. That's over in Alaska, and here's a picture of the biggest mountain right there. Let me zoom you in there. There's the biggest mountain in the United States. Its height is about 3.84 miles from the ground. And suppose you go on there and you start climbing it, and you climb it and you climb it, and when you're way at the top, you look to see, hey, how far can I see? And you realize that you can see all the way to Anchorage, Alaska. This is Anchorage. And you're right here, you're about 3.84 miles above the ground. And then you start to think, well, how come I can see all the way to Anchorage and no less than Anchorage? And you think, how far is Anchorage from the top of Mount McKinley? And suppose you estimated it's about 174 miles. That alone, my friends, just by climbing the United States' biggest mountain and glancing at it at the horizon and trying to see how far can you see in the horizon, that alone is enough to see how big what the radius of the Earth is. Amazingly enough, because then you can play this Pythagoras game here. You imagine the center of the Earth is here, and you say, all right, this is what I'm looking at. I'm looking for x here, the radius of the Earth. And you think to yourself, well, I know this guy right here is x plus a little more, x plus 3.84. And I know that wherever I can see the horizon, that must make a 90-degree angle. Of course, I'm simplifying things because there might be a little hill here or whatnot, but just go with it, all right? Let's let that slide. And then you could play the Pythagoras game. The Pythagoras game would say, all right, this is x plus 3.84, for that's the height of the mountain. So this is the hypotenuse, and so Pythagoras would say x plus 3.84. That's the hypotenuse squared is equal to the sum of the squares of the other two sides. So that would be x squared plus 174 squared. Let me zoom out just a little bit so you can see the whole picture. And then you could FOIL this, and you really here all you have is an equation that we can solve. So I'll square this plus 2 times 3 times 84 x plus 3 times 3.84 quantity squared, and that's equal to x squared. And 174. Let me do that real quickly in my math hands brains. That would be 30,276, I think. All right, and that gives us the following equation. We got to resolve this equation. I could subtract x squared from both sides. That one is gone, and that one is gone. And that leaves me with the following equation. That leaves me with 2 times 3.84x plus 3.84 squared is equal to 30,276. That's a little better. It seems to be a linear equation, so I can move this over to the other side. That will give me 2 times 3.84 times x, and that would be equal to 30,276 minus 3.84 quantity squared. That's 2 times 3.84 times x is equal to, I'll clean this up. So we divide both sides, or first we subtract 30,276, take away 3.84 squared. This is about 14, so that leaves us with about 30,261.25. Next we divide both sides by 2 times 3.84. Divide that by 2 times 3.84, and that gives us x. X is equal to approximately 3,940. That, my friends, that's just a rough estimate. Of course, the units were miles for this x right here. How big the Earth is, or the radius of the Earth. It's a cute little example of something kind of like real life, but it's a fun application of the famous Pythagoras theorem. And every time you know 2, Pythagoras tells you the third side. Or in this case, every time you've got all sides but one variable, Pythagoras will settle it for you. Alright, I hope you guys enjoy this. It's time for you guys to do some work, and we'll see you guys here next time. Peace.